So welcome back and good morning. And today we'll see the major topic in the fourth module, that is how to solve a difference equation, not differential equation, how to solve a difference equation. See, already you might have learned solution for differential equations in during your course S3 course, where you had a paper itself named differential equations. So there you have seen differential equation solutions using complementary function as well as particular solution. That was for continuous time signals, but the same thing will happen, same sort of equations will also appear in digital domain or discrete domain, and that equations is called as difference equations. So instead of differential equations in continuous domain, in discrete systems or digital systems, you have difference equations. So difference equations is that it includes digital terms and digital signals, and we have to solve that. We have to solve in the sense that we have to find what is there. We have found what was y of t. Here we have to find what is y of n given an input to a system. So that is all about difference equation. If you remember the method we followed, if you remember the method we followed to find the complementary function and particular solution, then it is very easy to understand this one also. We'll be moving in similar lines during this lecture. You will understand. If you remember that, you'll easily understand how simple it is to solve a difference equation if we have learned differential equation solutions very perfectly. The same method, the same way we'll be following here also. Nothing different. Only difference is that instead of differential equations, we have difference equations. Instead of continuous time signals, we have digital signals. That is all. Okay. So let me start. That is, in the first two lines itself, we can see two equations. That is, y of n is y of n minus alpha into y of n minus 1 equal to x of n, and the next equation is y of n is equal to x of n plus x of n minus 1 plus x of n minus 2. See, the first one is called a recursive equation. That is why I have marked R there. Recursive equation. Recursive equation in the sense that total equation represents a system. So that system has a feedback. That is why it is called a recursive equation. How can you understand that such a system has a feedback? See, there you can see that there is a term like alpha into y minus 1, yn minus 1. Yn minus 1 is nothing but the feedback. That is, output is fed back. Okay, that is why that is not the present output, but the past output is fed back, so that you'll get the present output, that is y of n, and that is why it is called a recursive equation. So recursive equation is nothing but a system which is having a feedback. So you can straight away understand from the equation that this has a feedback. That is why y of n minus 1 term is there. But whereas when you look at the second equation, you don't find any feedback from the output, but you can see that inputs are there, which are present inputs as well as past outputs. Okay, so the second one is called a non-recursive equation where we don't find any feedback. Okay, and the next thing is that both equations represent causal systems. So what are causal systems? System which depends on present as well as past inputs. So you can see that two equations have present as well as past equation. The first equation have only present input, but the second equation has present as well as past inputs. So both are causal system. Both represent causal systems. Equation in the sense represent a system. Okay, that is one thing you have to keep in mind. That is the importance of equation also. That is why whenever we have a physical system, if we want to analyze a system, we have to convert or model the equation, model the system mathematically. So how do you model a system mathematically? Representing either in the form of differential equations or difference equation. Okay, so in general, you can write the difference equation as y of n plus b1 y of n minus 1 plus the last term will be b and y of n minus capital N. For that polynomial itself, the order is capital N, whereas for RHS you have a naught x of n plus a1 into x of n minus 1. Likewise, it goes up to am x of n minus capital M. For RHS, the order is m. So typically a question will arise, which is the order of the system, because in total you are considering a system. LHS equal to RHS will be a system. So what is the order of the system? Order is that whichever is greater between m and n will be the order of the system. If m is greater than n, that is the order of the system. If n is greater than m, that is the order of the system. Okay. And one more thing you have to keep in mind is that whenever you have a system, you may have coefficients, um, coefficients with yfn. Suppose if that equation is b naught into y of n plus b1 into y of n minus 1, likewise. So if that is the case, you have to make the coefficient of y of n as 1. How can you make the coefficient of y of n as 1? If the coefficient of y of n was b of b naught, then you have to multiply that equation throughout by b naught, so that you can make the coefficient of y of n 1. So that should be kept in mind. So whenever you write an equation, even if you find some coefficient before the first term, before y of n, you have to make the coefficient 1 by dividing throughout the equation by that coefficient itself. So there you can see that I have written the general form, keeping in mind that the y of n coefficient is 1. Okay. Now, for a causal system, y of n can be determined for any value for n which is greater than or equal to n naught, but on one condition, that the initial conditions prior to n naught are known or given. Okay, that is, you can find y of n. Sorry, one minute. You can find y of n for any values of n greater than or equal to n naught. N naught is a general term. It can be 0 also. So, but you have to, the system has to be supplied or given with initial conditions prior to n naught. Okay. So in general, y of n is a function of past outputs if it's having a feedback, and present or past inputs also. So x of n. Okay. And this one method we'll learn that now, that is, the solution y of n is nothing but the sum of complementary function, which is yc of n, and particular solution, that is yp of n. So yc of n represents complementary function, and yp of n represent particular solution. So what is yc of n? That is complementary function, which is determined with input is equal to 0. That is, yc of n is found from initial conditions. For an output to generate, there should be some sort of an input. Either it should be an external input, or that should be from the initial condition. Initial conditions are also input. Okay, that is the initial charge in a capacitor. That is an initial condition. Okay, or the current stored in the magnetic field of an inductor. That's an initial condition. Okay, so yc of n, or the particular the complementary function, is determined with input is equal to 0. That is they are determined with initial conditions, from initial conditions, whereas particular solution is actually with the input. Okay, now yc of n, let's start with yc of n. How do we find yc of n? Okay, yc of n in general will have, I'll just explain all these things in a very simple manner so that you can easily understand and solve any problems. This lecture will not be that lengthy also. So yc of n general will have capital N number of constants, because we are taking the LHS alone and equating that LHS equal to 0. We don't consider the RHS there. So take the terms of the LHS and equate to 0. So the order of that equation is actually capital N. So that naturally brings in capital N number of constants, because it have that equation, if you solve, will have n number of solutions. If the order of that equation is capital N, then n number of constants as well as capital N number of solutions. Okay, let us try a solution that is equal to lambda raised to n. Let us imagine that what is complementary function? Complementary function yc of n is that we take the LHS alone, equate that to 0 and then we are trying a solution lambda raised to n. So if I substitute instead of y of n is equal to lambda raised to n, we are ultimately finding lambda raised to n. That is yc of n we are taking, and we are applying a solution. Okay, so if lambda raised to n is that solution, we substitute in that equation. When you substitute, the first term becomes lambda raised to n, the second term becomes plus b1 lambda raised to n minus 1 plus likewise the last term will be bn lambda raised to n minus capital N, which is equal to 0. Now if I take, this is an important step, if I take lambda raised to a small n outside, and that can be cancelled, lambda raised to n if I take outside, and that, because that if that is equated to 0, then that will disappear, and then multiply the equation throughout by lambda raised to capital N, I'll get a result like lambda raised to capital N plus b1 lambda raised to n minus 1 plus bn, that is equal to 0. So that is called the characteristic, the right hand side of that is called the characteristic polynomial, and the entire thing is called the characteristic equation. So we started with the particular complementary function, we took the LHS, equated that to 0, and tried a solution for y of n is equal to lambda raised to n, and we got the characteristic equation like this. Why it is called a characteristic equation? Because if we solve that characteristic equation, we'll get capital N number of roots. Okay, so roots of that characteristic equation will determine the nature of that system. So roots will determine the character of that system represented by that equation. That is why roots play a very important role. So naturally this equation is the order of capital N, so you can expect n number of capital N number of roots, which are given by lambda 1, lambda 2 up to lambda raised to capital N. Now I told that when you have capital N number of roots, then you can expect capital N number of constants also. So the total, so that constants will be alpha 1, alpha 2 up to alpha raised to alpha suffix small n. Actually it should be capital N also. Okay, n number of constants. So if I do that, it will be alpha 1. So what will be the form of the complementary function? YCFN will be, okay, add all the solutions with that constants. That is alpha 1 lambda 1 raised to n plus alpha 2 lambda 2 raised to n plus alpha n lambda capital N raised to small n. Okay, so there you can see that all those constants are distinct. Okay, all those constants are different, and also one thing, you are saying that the roots lambda 1, lambda 2 up to lambda capital N are distinct. Okay, if that they are all distinct and different, this is the solution of the complementary function. Okay, there can be a situation where the sum of the roots are repeated. Likewise, you can see the bottom of the page, that is YCFN is equal to lambda 1 raised to n into alpha 1 plus n into alpha 2. Okay, sorry, that is if some of the roots are repeated, let us say that lambda 1 is repeating L number of times. You can see on the screen, that is bottom of that page, that is lambda 1 is repeating L number of states. So total number of roots does not change, but the root lambda 1 is repeating L number of times. So after that, the next root will be lambda L plus 1, the next root will be lambda L plus 2, and finally the last root will be lambda capital N. Okay, totally capital N number of roots should be there, because the order of that equation is capital N. Okay, so if lambda 1 repeats, suppose if lambda 1 repeats capital N number of times, this is the form of the complementary function, because that lambda 1 which is repeating L number of times is taken by the first term inside the bracket, that is lambda 1 raised to small n inside the bracket alpha 1 plus. So alpha 1 is only there because alpha 1 is being multiplied by n raised to 0. That n raised to 0 is 1, that is why you don't write n raised to 0. So but n raised to 0 is there, but we don't consider that because that is equal to 1. So alpha 1 plus n into, that is n raised to 1, n into alpha 2 plus n square alpha 3. Likewise, the last term will be, we have considered the first term as n raised to 0, that is why the last term will be n raised to L minus 1 into alpha L. Okay, so the last alpha will be alpha L, because we have alpha lambda 1 L number of lambda 1, so that the last term will be alpha L, because L number of alphas or constants will be there. Okay, and after that it's all the same way, that because all other roots lambda n L plus 1, lambda L plus 2, likewise up to lambda n are distinct, so you can follow the same method, that is alpha L plus 1 lambda L plus 1 raised to n plus alpha n lambda n raised to n. Okay, so this is the case if some of the roots are repeated. And then this is all about complementary function. We'll see some more things when we go into the equation problems, but starting condition, this is enough. And what about the particular solution? See, particular solution, the very important sentence is that particular solution is in the form, is in the same form as that of the input. I repeat, particular solution is in the same form as that of the input. That is, you can see that if the input x of n is a constant k, then I told that the particular solution is the same form. Then the particular solution yp of n should be equal to some other constant. It's a constant, but some other constant k1. Then if x of n is sinusoidal, that is a cos n omega naught plus theta, then yp of n is also sinusoidal or cosine wave, that is, but some other cosine wave, that is b, that is some other constant b cos n omega naught plus, it's instead of theta we have some other phase, that is phi. Okay, and if x of n is alpha raised to n, if input is alpha raised to n, then the complementary function will be c alpha raised to n, that is some constant c multiplied with alpha raised to n, where alpha, that is very important, where alpha is not equal to lambda I. Okay, that is that alpha should not be any that should not be any root of that characteristic equation. We'll see two cases in the later stage of the video. Okay, so this is all about the complete description, and we see the first problem, that is y of n plus 0.5 y of n minus 1 equal to 2 u of n. So we are describing a causal equation. Here n naught is, we in the initial descriptions I told that we can find the solution for any values of n greater than n naught. Here the n naught is 0 because we are considering u of n there, a causal system. Okay, and you can see that the order of that system is 1. That's a first order system because you can see that the highest term is y of n minus 1. So that is a first order equation. So in order to determine the solution for a first order equation, we should have what? You should have one initial condition. So I told that all the initial conditions prior to n naught should be non. So prior to n naught, prior to 0, there should be one initial condition. So prior to 0 there is minus 1 is there, and that is why we have y of minus 1, and that initial condition is given as 2. Okay, now you have to apply the equation, that is you have to first find what is complementary solution, that is yc of n. Okay, so take the LHS alone, that is y of n plus 0.5 y of n minus 1, equate that to 0 and try a solution lambda raised to n. So when I try a solution lambda raised to n, y of n can be replaced by lambda n plus 0.5 into lambda raised to n minus 1 equal to 0. And if I take, okay, well I explained, you can take lambda raised to n outside and equate that to 0. And then you have to multiply the whole thing by lambda raised to capital N. Here capital N is 1. So multiply by lambda. You'll get it as what? You can see that lambda raised to n is taken outside. It becomes 1 plus 0.5 into lambda raised to minus 1. That is equal to 0. You can cancel lambda raised to n. Then you multiply the whole equation by lambda. Then you get lambda plus 0.5 equal to 0. And what is lambda? Lambda is equal to minus 0.5. So since it is a single order system, first order system, number of roots is also 1. So my root of that characteristic equation is minus 0.5. So what is the form of the complementary function? Form of the complementary is that alpha 1 into lambda 1 raised to lambda 1 raised to n, alpha 2 into lambda 2 raised to n. Here we have only one root, so one constant, that is, let us take that constant as k. So yc of n is k. It's on the top of the page, that is page number 32, top position. Yc of n is equal to k into that alpha raised to n. Here alpha is lambda raised to n. Here the lambda is minus 0.5, the raised to n. That is yc of n. Okay, but let us keep that yc of n as such. We'll go to the particular solution. The particular solution is in the same form of the input. Here you can see that input is u of n. U of n is nothing but 1 for n greater than or equal to 0. So we are considering only instances from n greater than or equal to 0. So you can avoid that, and you can replace u of n simply by 1. So 1 is a constant. So I told that the particular solution is the same form of that input. So as input is a constant, my particular solution also will be some other constant. So let us take that as k1. So yp of n is taken as k1. So we take the entire equation, that is y of n plus entire question once again. Y of n is plus 0.5, y of n minus 1 is equal to 2, and we take the particular solution as another constant k1. As it's a constant, every term in that equation can be replaced by k1 itself. So k1 plus 0.5 into y of n minus 1 is again k1, because that's a constant. K1 equal to the same input 2, because on the RHS you have the same input. I also already told that the particular solution is determined from the input, so you have to keep the input. But whereas why we equated the RHS equal to 0 for finding complementary function, because in the right hand side you have terms of input. The input is considered as 0. That is why we equated that to 0. Okay, here we have to take account the equation, account the input. That is why RHS is taken into account, that is 2 is there. So from here you have to find k1. So whenever there is a constant, there is no need to change the k1 value when you see y of n minus 1, y of n minus 2 likewise. So you find the value for k1, you got it as 4 by 3. Okay, now after getting yp of n, okay, what is yp of n here? It is simply 4 by 3. It's a simply constant. Input was a constant, you get another constant 4 by 3 as a particular solution. Now what you have to do is y of n we know, that is yc of n plus yp of n, that is complementary function plus particular solution. You add that. We know that yc of n is nothing but k into minus 0.5 raised to n, plus what you get for particular solution is 4 by 3. You add that. After adding that only, you have to determine the value of k, that is alpha. Instead of alpha we have substituted k here. So you have to find the constants of the complementary functions only after adding the complementary function with the particular solution. So you are adding the entire thing, that is k into 0.5 raised to n plus 4 by 3, and then I told that the constants are evaluated from the initial conditions, and then after adding the complementary function with the particular solution, apply the initial conditions, and then you have to find k1, not before that. Naturally there will be a tendency to find the constants of the particular complementary function before adding that with the particular solution. That there will be, and that will result a wrong result. That will result in a wrong value. So after finding the complementary function, add that with particular solution, and then apply the initial conditions to find the value of the constants in the complementary function. That is, here it is k. So y of minus 1 is 2. Equate that is 2. That is n is substituted as minus 1. That is 2 is equal to k into minus 0.5. Instead of n, you have to substitute minus 1 plus 4 by 3. From there you can find k, that is given as minus 1 by 3. So everything is found out. So y of n is nothing but minus 1 by 3 into minus 0.5 raised to n plus 4 by 3. Get the complete solution. The first one is the complementary function, and 4 by 3 is a particular solution. Now suppose I told that in the beginning I told that alpha raised to n should not be equal to any lambda I. Okay, if that is equal to lambda I, what is the case? You can see that. See, I take that same question, LHS remain the same, but instead of that u of n, or 2 into u of n, I have minus 0.5 raised to n u of n. Instead of u of n, my input is minus 0.5 raised to n u of n. And naturally, as the LHS is the same, the complementary function also will remain the same. What will be the complementary function? K into minus 0.5 raised to n. That is the solution. That is already done with, and that is already written there. Now, you can see that my input is in the same form as the complementary function. Okay, that is, it is 0.5 raised to n. Here also, that is, complementary solution is also 0.5 raised to n. Okay, so here you can see that you cannot do with the normal procedure, but one simple thing you have to by heart. You just understand and remember that simple thing is that I told that the particular solution will be should be the form of the input, but here that is not the case. We have to deviate slightly. The thing is that you should write, that is, instead of minus 0.5 raised to n, multiplied with some other constant k1, you have to multiply that with n also. So k1, additionally just write n, then 0.5 raised to n, minus 0.5 raised to n. That is only difference. Okay, that is whenever the particular solution, whenever the input is in the form of the complementary function. Sorry, the complementary function. When the input, you can see that minus 0.5 raised to n, u of n is in the form of the complementary function. If that is the case, then you cannot apply the normal method. This is a special case, and there you have to go with the particular solution like some constant k1, then all other terms remain the same, that is minus 0.5 raised to n will remain the same. Multiply the whole thing with small n, that is yp of n is k1 into n inside the bracket minus 0.5 raised to n. Okay, then you apply this yp of n in the whole equation. Okay, that is, this is a solution you have to apply in the whole equation. That is, write the entire equation, entire question once again. Instead of y of n, you can substitute k1 into n minus 0.5 raised to n plus 0.5. Then you have, instead of n, you have n minus 1. So n is replaced by n minus 1 multiplied by minus 0.5 raised to n minus 1 equal to the same input, that is 0.5 raised to n u of n. Okay, and you simply solve that equation. There is only one unknown, that is k1. You can get it as k1 is equal to 1. So if you substitute k1 is equal to 1 there, you can get the particular solution, that is n into minus 0.5 raised to n. Now we have to add the complementary function, which is k into minus 0.5 raised to n, and the particular solution, that is n into minus 0.5 raised to n. If you take minus 0.5 raised to n common, you will get inside the bracket k plus n. And after that, you have to apply the initial conditions to determine the constant k, which is of the complementary function. And y of minus 1 is equal to 2, because we didn't change the question, and the initial condition also will remain the same. So equate that and get the value for k. You'll get k as 0. So you can say that for this case, the complementary function is absent. Okay, you have only the particular solution. Likewise, you just solve the question given in page number 33, and at the end I have replaced the same question with x of n is equal to 2 raised to n u of n, and you can see that it also will the particular solution for that, because you can see that the complementary function in the previous question, the complementary function, this question, the complementary function is having a root 2 raised to n. So my input is also 2 raised to n. My complementary, one term of the complementary function is also 2 raised to n. So you cannot apply the normal method in the second case if the input is 2 raised to n u of n. There, the particular solution should be what? Some constant k1 into n into 2 raised to n. That is all. And you have to follow the normal method. And you have to solve these two problems in this class. And I'll ask the solution during the next class, that is on Tuesday. Thank you so much.